The sun is the largest object in our solar system, and you see it almost every day, but we probably never thought, where does the sun get its energy? That's the question we are here to answer today. So where does the sun get its energy? Well, first of all, the sun is made up of mostly hydrogen and helium, 70% hydrogen and 28% helium. A commonly known myth about the sun is that it's a big ball of gas. It's actually made up of plasma, the fourth state of matter. You know when you heat up a solid, it turns into a liquid, and when you heat up the liquid, it turns into a gas? Well, if you heat up the gas, it turns into plasma. You probably learned there are only three types of matter. This is the big lie your elementary school teachers taught you, because over 99% of the visible universe is made up of plasma. The energy is created when the hydrogen protons collide with each other and fuse to create helium. In the process, creates energy. This is called nuclear fusion. The protons normally hit each other, they bounce off each other, but they're moving so fast to where they can't bounce off each other. In this situation, speed depends on how hot the protons are. According to Universe Today, the center of the sun is the hottest part of the sun and is where most of the energy is created. The center of the sun can reach temperatures up to 15 million degrees Celsius or 27 million degrees Fahrenheit. The sun accomplishes getting this immense heat from being so large. The sun is 1.3 million times bigger than Earth and creates so much pressure in the center it rips apart protons from electrons and creates a lot of heat. Once the energy is created, it rises to the surface and takes 8 minutes to travel from the sun to Earth. Side note, if there was air in between the sun and the Earth, the nuclear fusion would be loud enough to hear at about 125 decibels. It would be the loudest thing here every day. This would be about the same as hearing an airplane take off. It would be hard to hear anything else or even have a simple conversation. Stars have life cycles. They are born, live, and die. When the hydrogen protons in the sun collide with each other and create helium, they lose some mass in order to make energy. A star is made when a bunch of gas comes close together and the gravity from their own mass starts to pull them together. Our star started as a yellow dwarf star. In the core, it fuses hydrogen to make helium. The star eventually will run out of hydrogen. It will eventually fuse helium as its fuel source and turns helium into carbon and oxygen. This creates a lot more energy. Since using helium as a fuel source creates more energy, the star will start to expand and will become a red giant. When the star expands, it can have a diameter of 620 to 621 million miles. This will eat up Mercury and Venus and possibly Earth, but it will become too hot to sustain life on Earth, and we will all die. But luckily, this is 5 billion years from now, and we'll all be dead by then anyway. As said before, the sun creates energy through nuclear fusion. Nuclear fusion is the ultimate form of producing energy. It is clean energy, and a cup of seawater can produce as much energy as a barrel of oil. It has no chance of a nuclear meltdown. Seawater would be a good fuel source because it has a lot of hydrogen, and all the seawater on Earth can power Earth for about 30 million years. If we had fusion technology, we would have almost limitless, cheap energy to power the entire world for millions of years. But what's the catch? The problem is that protons have the same charges. Protons are positively charged and don't like other protons. But in order to create fusion energy, the protons have to get close enough to where the nucleus of the protons touch. It would be very difficult to make a system to do this, because it would have to make the protons very hot and pressurized, and have this contained for a long enough amount of time. We couldn't use the system the sun uses, because that would be very dangerous for the Earth, and a head of a pin of the temperature at the middle of the sun would kill everyone in a 1,000-mile radius, according to the universe today. So we would have to get very creative in order to make fusion energy. We would have to spend billions of dollars to develop this energy, which might not even be possible. But is spending some money worth the reward of infinite energy? Maybe we should cut our losses and invest that money into other forms of energy. Or maybe, just maybe, when the payoff is infinite clean energy, the reward might be worth the risk.